Tremy concrete, even with only 14% cement, we were still getting very good strength gain with our Tremy concrete mix designs. Here's limestone powder. It's just mined and it's ground into a powder, and it can promote the formation of ettringite, which is not a problem so long as the concrete is fresh. If it happens after the concrete is hardened, it can be a major problem as it expands, but actually it's kind of good to get the ettringite done while it's fresh, because then there'll be less propensity for it to react later on. It also decreases permeability here, so it increased the cohesion, it reduced our bleeding, and it made our consistency very good for the Tremy concrete. Microsilica fume, it's much finer than all the other particles, so it can promote many sites of nucleation for the hydration product to grow, which winds up with a finer microstructure. It has a nice water binding capability. It can reduce the segregation and bleeding, and small additions produce denser concrete with a better bond to the aggregate. It can decrease some of the calcium hydroxide that can be a weaker product. So this just gives you an idea that it gives you a lot more nucleation sites, so it can be a finer type of a cement paste structure. It gives you better strengths and better permeability values. So this is chemical admixtures. We're fortunate that we have high-range water reducers these days, but we think it is valuable to blend them with a low-range water reducer. It can extend the slump life, and it can be more economical that way. And using the anti-wash admixture, as I said, it can improve the strength of the concrete, get rid of the breeding bar effect. And here for the Tremy concrete, it allowed us to have higher workability and still achieve consolidation underwater. So here's air entrainment. We did have, I think, up to 6 to 8% air entrainment here. As you put in air entrainment, you can take water out, and still maintain the same workability. So it can be cost effective in that regard. So even though we don't have much of a freeze-thaw problem under the river, it still it can improve workability. So you can see it can actually produce a little bit better flow patterns. These are just different ways of getting the concrete to the site. You can either have a floating batch plant or take it by a transit mixer, or in this case they're actually wind up pumping it through a pump line to agitator and then placing it down the line. You have to start off the placement with different ways of sealing the Tremy pipe, either with a cap or a plate, or you can also use a pig, but here we're using a plate on the end with tie wire. So this just shows it getting started. You need to seal it there in the bottom to stop it from mixing with concrete, so you always keep the end of the pipe buried. As I said, it builds up and then flows out. If you have latents, you want it to move all in one area so that you can remove it after the placement. So this gives you an idea of one of the major reasons for using such a low cement content was that we have a very thick placements of Tremy concrete here. This is, I think that's close to 60 feet from here up to here. So there was a large amount of fresh concrete for a massive pour. It's important to control the thermal stresses. So we did a non-linear incremental structural analysis. All the properties of concrete are non-linear at early age, and so we have to have varying the stiffness of the concrete, the Young's modulus, so the strength is changing, the tensile strength is changing, the heat generation patterns go into the analysis on the computer. We have to match the sequence of construction with the different lifts going in at different times, and simulating the ambient temperature from the river water during the summer and the winter to match what our placement plan. They're placing now in the fall. So this was a typical output. You can see the temperature pattern. The red is, of course, hotter. This is after one day. All the tremmy's not in place even after the end of one day, so this is already starting to hydrate down here by the time we're up to the top. So you can see normally it cools around the perimeter while it's still heating and expanding on the inside. So it expands on the inside, then it creeps, and then when it cools, it pulls back in, puts the outside into tension. So you have to, once you get these temperature patterns, and you have to do a strain and stress analysis. So this is, then when you get the strains and stresses, then you can produce predictions about cracking. So you just monitor the change in the tensile strength of the concrete with age, and fortunately we have a shell. So that has a relatively high tensile strength because it's precast and prefabricated and highly reinforced. And as you would expect, the crack potential is highest right where there's a reentrant corner, stress concentration, and this just shows that there's a percent of the crack criteria, so that's just under the crack criteria there, 99% of the crack criteria. But even if it does crack, most people assume concrete is cracked. That's why there's reinforcing across it. But the Army Corps wanted us to try to characterize the widths of the crack and what they'd be opening or closing if they did form, and how fine they'd be. So we did do that analysis. And also they wanted to see the deformed shape of the shell as it was expanding and contracting with time. So we had that, including the shrinkage, the natural shrinkage that was going on too. So it's not just thermal, it's also, as concrete hydrates, there's a chemical shrinkage. Of course, since it's underwater, there's no drying shrinkage going on. They had two full-scale Tremy mock-up placements. So this is after the shell's been stripped, and this is showing the concrete being placed. You can see the outline of the shell. It had, in those particular shells, it had beams in it, and the concrete went all around the beams and filled in, and there was a good bond. They took cores through the shell and through the concrete, and there was a good adhesion between the shell and the reinforced and the Tremy concrete. So you can see after they removed all of the forms that matched the beams, all the concrete in here was perfectly matching the surface of the underside of the shell, with very little bleeding in this case. So this shows some of the overflow. We inside of the shell, we required the contractor to put in more Tremy concrete than the volume was required, so some of the latents would flow out the top. And in this test, after it flowed out, it wasn't contained and it mixed with the water, so there was more latents there than what was really the case in the river. And in the river, it flows into the legs of the lifting frame so that it doesn't mix with the water and affect the environment. Okay, so Tremy concrete, effective way, efficient way for the Olmsted Dam to be built underwater. We've had high volumes of granulated blast furnace slag to reduce the heat and improve the workability. And as I said, it's been demonstrated to be quite effective in practice, because it's due to the rate of funding. They're not building it as fast as I might have thought would be optimal, but so they only do so many shells a year, and then they start over again when the funding stream starts. So that's why there aren't more shells installed quite yet. Now this is another Army Corps project. Instead of being the top priority civil project, this is the largest design-build civil works project for the Corps. So it's the Inner Harbor Navigation Canal, that's the IHNC, Hurricane Storm Surge Barrier, and I'm just focusing on one part of it. There were 3 navigation gates, and this floating concrete barge gate uses high-performance lightweight concrete. So I'll give you a brief overview of the project so you can see where it is, and then we'll focus on the concrete behavior. So here's the introduction. So this project goes across what they call the Golden Triangle, which was where the worst flooding was in New Orleans after the Hurricane Katrina. And we needed to come up with a solution. It was design build. We're working with Shaw, E&I, Environmental and Infrastructure. And it goes across the Gulf Intercoastal Waterways, which is goes from Florida all the way to Texas. It has a lot of barge traffic through it, and we have to maintain that during construction. So normally during operations there'll be a sector gate. The Army Corps liked that for ease of maintenance and operation. But while we're building this, we had to have a bypass gate, and the Corps wanted that to be permanently operational. In the bid, it was going to be a temporary gate that was just open during construction and then shut, but they wanted to have it open all the time to improve the circulation of water back behind the barrier, which meant that we then had to now design this to function for a 50-year operational life and a 100-year service life, so that they could extend it operationally by adding some maintenance. And another consideration of this, although the Army Corps funds it and builds it, then they turn over control of it to the local flood authority, who has almost no maintenance money. So when you were to talk about the option of doing some sort of impressed current cathodic protection afterwards, that was unacceptable. So we had to do something that would guarantee the 100-year service life with no further maintenance besides inspection. So in this gate, the navigable pass on the GIWW was 150 feet, so the barge gate was 190 foot, so it could bear up against the abutments and take 25 foot of, well, there's a 22-foot head of storm surge that comes in with the hurricane, and then the waves build up on top of that another 7 feet. And you can see the base width here is 62.5 foot. The height is 43 feet because you have to go down below water level for provide well, the bottom of the sill here is at minus 17 feet. I think the bottom of the sill above that, there's a ledge that it bears against at minus 16 feet. And for a variety of reasons associated with the changing of the criteria from it being temporary to being permanent, weight became critical. So we went with lightweight, high-performance lightweight concrete, which has a benefit that also has very good durability because it has very low permeability. So here's the barrier. You can see it on Google Earth. Here's the GIWW, Gulf Intercoastal Waterways. Right around the corner here, there's a NASA site where they load up the solid rocket fuel for the space shuttle, and then they take it down along this waterway to Cape Kennedy. And a lot of petrochemicals go along here. This is the Mississippi River Gulf outlet that was decommissioned. Here's one navigable gate, the Bayou Bienvenu. And here are two gates. These are the abutments where the barge gate will go, the bypass gate, and this is a 2-mile-long batter pile flood wall that we were the lead designers on. This is the cofferdam from September, just last month, for the barge gate, and this is the traffic goes through this pass at the moment. And they're building the barge gate in a floating steel dry dock in Sulphur, Louisiana, several hundred miles away. It was an existing dry dock that the contractor got, and he thought that would be a good way to launch the barge gate out of it. So here it is, 190 foot, 62.5 foot wide. That's the keel slab. In April, here's in June 2010, with the lower portion, there's 3 levels of decks. There's the keel slabs, the bottom level, this is the mid-level, and then there's the driving surface up above. So you can see this is as of August. I believe they're about 2/3 of the way through this mid-deck